Hello everyone. Today I'm going to be talking about what I'm calling medium-term AI safety. So what does medium mean? It is actually a pretty broad-ranging medium. So let's talk about the nature of what AI is. So we really want it to be a kind of multiplier for whatever it is that we want. So and this is kind of true for machines in general. So for physical machines, if we have a tractor, or if we have a plow, we'd want it to do what a human would have done, but much better, much more automated, and much more efficiently, and ideally be able to do entirely new things at the scale. So within artificial intelligence, there are enablers, core key underlying capabilities. So this is modeling capacity, modeling of the world, and as we increasingly go to open world models, this could include much more statistical representations and try to represent uncertainties about the world. And then we have the action space range, so doing things that whether humans can do or machines are quite specifically capable of doing. So when these are combined, we get new capabilities overall. And then these can, in turn, be new actuators or new actions. So things like making phone calls. This obviously involves understanding speech, being able to have language models to do this modeling of the relevant domain. But then there are actions within that as well. So as we add these new sort of modular capacities on, we should keep in mind that this action space range grows quite a bit. And implicit in these actions, as the open world model kind of grows, is the ability to influence people in a way that Eric kind of mentioned, that there are these very complex paths within the world, within these decision trees and action trees that can involve the environment, can involve humans interacting with the systems, and can involve different pathways of information through those systems. So overall, this is basically leverage. And as anybody who's traded in the markets understands, having a little bit of leverage in the right direction can lead to very good things. Having leverage in the wrong direction can lead to very bad things. And the more leverage that you have, the more important it is to have things go in the right direction and not the wrong direction. You have much less tolerance for error, and things like value alignment or having beliefs or values that are in line with what it is that is actually going to be levered and made very kind of geometrically just happen in the world is going to be more important. So various ways of confusing the system include under constrained cyber-physical context. As the previous speakers have mentioned, there can be a child kind of running out from the side of a road, or a ball thrown into a car's windshield, and one can't necessarily think of all those different things beforehand. If folks are trying to make actual specific rules to deal with all these things, or to construct a training set, it's very difficult or impossible to think of all the things that one has not thought of previously. This is kind of the nature of what Isaac Asimov has written about with his 3 laws. One can't make enough laws to actually accommodate for all the complexities of the real world. Another type of confuser is what we might call instrumental subgoals. So for any given goal that a system has, things like getting additional resources to achieve those goals, or the continued propagation of that agent, are actually important from the system's perspective to achieve those goals and to achieve them better and to continue achieving them in the future. So as systems get more complex, as systems are able to go beyond the understanding of people, these things become relevant. So let me go on here. So as Stuart Russell likes to say, with value misalignment, a model of something that you're trying to have the system do can go to extreme values in dimensions that you're not actually including in the model. And this leads to very unreal, very negative policies oftentimes when computing what might be thought of as quote unquote an optimal policy when those variables are not taken into consideration. Other types of confusers happen when there's leakage of control information going into the system's models. So this is a little bit similar to what Eric was mentioning earlier, that things like reward precursors, life cycle events, reset or recharging or activating or deactivating certain command paths can creep into whether explicit or implicit models of the world. And when we're talking about something like Deep Blue with a very, very constrained model of the world, this is not relevant at all. But if we're talking about something that's much more general, that can explore the world and it can explore itself, these become much more relevant because exploration of the world in a very unconstrained way can lead to essentially self-discovery, which can lead to things like reward hacking or can lead to things like a loss of control potentially. And these can interact with poor value alignment in a way that can lead to the AI overstepping potentially. So just as kind of a toy example here, if we're trying to surveil a black box system where, in this example, the AI is trying to put only a single cube or here into the black box in the corner, the AI can, if it receives a reward for when it puts that cube into that box, and then we have this external controller which shuts down the AI when we see that it has put one cube into the box, it can block that surveillance channel and keep on putting additional boxes into that hole. So there are various types of accelerators that can lead to these various kinds of confusion happening more rapidly. So systems grow in complexity beyond human understanding. The ability to have oversight is more and more limited as these systems become so complex. So ideally, we would want humans to have oversight over these systems, but that becomes complex. So as we cede more control of these systems and we become more dependent on them, choosing to scale back what the systems are capable of doing in terms of what they're authorized of doing might become politically or economically difficult. There are also new types of security issues that were raised earlier. And there's also the aspect a little bit later on, perhaps in a few decades, of recursive self-improvement. So once domains open up to include more and more subdomains, and once AIs are able to pick up new domains much more quickly and integrate them with other domains that they know, science and engineering will eventually be on the table. So as we have more and more greater amounts of leverage in these systems, we'll need greater kinds of control. So broadly speaking, verification, validation, security, and control form the structure or the basis of these various types of remediation. I'm going to drill down quickly into what some of these are. So we can think of some of these subtopics as forming a conceptual spectrum of what would be needed to really have what we might call robust or aligned artificial intelligence. So we'd like them to be less oblivious, so that's dealing with online distribution shift, being able to understand anomalies, being able to have a concept geometry that's compatible with human thought processes. So being able to have better introspection where humans and machines understand each other better, and being able to represent ethical concepts for what we might call value alignment. So alignment between what humans value and what the machines will value. Very much like those trade-off constants that were spoken of earlier. Alignment mechanisms include things like inverse reinforcement learning, being able to have actual mechanism design or protocol design where we can actually specify the bounds of how the AI will process things and flow. And we'd like to be able to quantify that. Mutual understanding comes when we're able to have these concepts of value that are whether implicit or explicit. And so implicit value alignment can also be from having the system learn from a large variety of sources of perhaps culture or whatever exhibits the actual values we'd like to have the system learn. We also need better accounting for causality. So being able to disentangle correlation from causation, being able to have audit trails within the AIs, and being able to have better communication channels where humans can describe what it is that they actually want, and the AIs can come back and disambiguate things. We'd also like to project behavioral bounds as we characterize the behavior of AIs. So this is actual formal runtime analysis, as well as perhaps psychological analyses of these large deep learning systems. We'd like to verify ML. So, for instance, if we have these statistical models that are built up as systems learn, perhaps we'd like to take a snapshot of a model and be able to do more deductive proofs over that model. So one example is if one takes a random projection of a statistical distribution or space and has a simplified view of that model, which then can be subject to SAT analysis or actual deductive proofs. Finally, we'd like to extend that concept of verification and statistical verification to self-modification. So similar to what the previous speaker was mentioning, one would like to keep a previous model around or previous priors around when doing a potential modification in order to see that the proposed modification is done in a safe way as the system is in an online context. And there are ways of making it safer beforehand as well. So statistical reasoning, or I should say logical uncertainty reasoning over proposed modifications over superior agents would be a necessary part of that for these developmental guarantees. So just kind of drilling in here, let's go to some of these. So caution in open world models is some work by Tom Dietrich, so using conformal predictions and apprentice learning for that. Brian Ziebart at Chicago is doing this with adversarial testing and adversarial risk minimization. So broadly, what we're looking at here are these ambiguity detections, feature identification, and characterization of this distribution shift, along with pervasive confidence quantification. Concept geometry, again, trying to have similar concepts to humans and being able to open up what's inside AIs for human understanding. This is done via introspection of what's going on inside AIs, for instance, looking at and visualizing what's happening inside deep networks, such as is happening at Georgia Tech, being able to have introspection within computational cognitive sciences, and analyzing the stability of neuromorphic motivational systems. We also want to consider explicit ethics. So being able to have systems evolve using a combination of game theory and mechanism design and Monte Carlo analyses, and being able to understand how ethical dynamics come into play in systems that evolve and participate in multi-agent systems. Also important here is the ability to refactor ontologies, to be able to re-identify things in the world, and to do that in a way that's not extremely self-centered. To be able to have essentially computational respect, computational humility. So part and parcel with that is incentivizing low impact in the world. So if we have a reinforcement learner that needs to explore, we'd like to do that in a way that does not change the world too much in negative ways. So it has to be aware of the impact that it's having as it's exploring, or as it's exploiting for that matter. The logical uncertainty awareness that I was referring to is if you know a lot, but you have very limited capacity to be able to follow all the logical entailments of those, you need to have some way of representing your expectation of what certain entailments are before you can actually get the chance to evaluate those. So cooperative inverse reinforcement learning is a way of modeling users, establishing representation of both the space that you're operating in and what people actually want to do in that space. Koslow counting. We can have both causal identification and top factor distillation come together for informed oversight of systems. So being able to have users be able to query a system on why it made certain decisions. And this, of course, ties into provenance of how systems got their data. Projecting behavioral bounds, we'd like to understand its decision theories, be able to project the computational complexity of various types of capabilities of these systems, and potentially bound their behavior and contain them if necessary. Alex Aiken at Stanford is working on this pretty cool probabilistic programming model that is also automating proofs, providing building blocks that folks can put together for more complex types of AI. Plotzer and verification through cyber-physical was mentioned earlier. Security evaluation is also very important, and this is part and parcel with the adversarial learning as well as learning optimization. And Stefano Ehrman at Stanford is working on expanded proof classes via what we might call probabilistic calibration, taking random projections over these statistical models and being able to do deductions over these distributions using, again, stat analysis and the actual types of software verification at that point that one can apply to what has historically been simpler types of systems, but this time on the actual learned models. And finally, these are being extended into self-modification work. So, thank you.